Alright, so we're going to pick up where we left off. We already discussed the idea of the cohesiveness of water and how that cohesiveness can interact to make the water more thermally stable, being able to moderate temperatures. So let's move on to the next concept, which is the fact that solid water, or ice, floats on liquid water. Okay? This is actually a very unusual thing. Most of the time, as you cool a body down, the molecules, again, temperature is just a reflection of how much the molecules are shaking. You shake less, 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 and less. You can pack things tighter and tighter and tighter together. And this is true for water until it reaches about 4 degrees Celsius. So as water cools down, it is becoming denser and denser and denser. When it hits 4 degrees, it is as dense as it can actually be. The colder it gets, it actually starts becoming less dense. And the reason for that is in water, an individual water molecule only has to have 3 hydrogen bonds, which means that the water can be packed tightly together. In ice, each water molecule has 4 hydrogen bonds, and they are relatively fixed. This causes the water to form this crystalline shape. And because of that crystalline shape, it is less dense than the liquid water. Now, you might ask yourself, why is that important? Well, let's just think about a lake, for example. Let's imagine that we're dealing with a lake in an area where it gets cold, it gets below freezing. As the water at the surface starts to freeze, if it didn't float, it would sink to the bottom. Eventually, that entire lake would be solid ice. Things like shrimp and fish cannot live in a lake that's solid ice. They can live in a lake because the water freezes and floats, so the frozen water actually remains at the surface and actually helps insulate the water down below because you have less transfer of that heat through that thick ice layer. Now, let me show you a video of what it looks like for water to freeze. Alright, so here we have a bunch of water molecules. They are vibrating and dancing around, and slowly you'll notice that they start fixing into the structure that has kind of a hexagon shape to it. You can see over here we have ice forming, ice forming, ice forming, and now the whole thing is fixed into ice. And here, when we have ice, we have all these open spaces that are kind of locked into place, and that is why frozen water is actually less dense. Alright, so finally, why is the fourth unique characteristic of water is that it makes it a very good solvent. Okay, so you might have to define a few terms here. So first of all, a solution is a liquid that is completely a homogeneous mixture of substances. So an example of this would be you take salt, you put it into water, that salt dissolves, and now every drop of water has the same amount of salt in it. Okay. More definitions here. The solvent is the dissolving agent, or the liquid. The solute is the thing that is being dissolved. Okay, so in our salt water example, water is the solvent and salt is the solute. When we refer to aqueous solutions, this is one where the solvent is explicitly defined as water. Okay? Now, let's think about why the fact that water is polar would make it a really good solvent. So over here we have salt, which again is an ionic compound. We have sodium that has been turned into a positive cation. We have chloride, which is turned into an anion, and it packs together to form this crystal. Okay? It is held together by these interactions of positive and negative charges. Well, look over here. The water also has its own positive and negative charges. Not full charges, but a partial charge. Consequently, when you have something like sodium on the surface here, water can come in and start interacting with it, specifically through the oxygen, and it can surround it and form something called a hydration shell, which will separate that ion from the crystal. The same thing is true over here for chloride, except for it's being connected with the hydrogen part of, or the positive part of the water molecule. And again, we're forming a shell, or a hydration shell around this. This can also happen in other types of compounds. So here we have a protein. A protein has a lot of different characteristics, but one of its characteristics is there are oftentimes regions on the surface that can form hydrogen bonds with water. Okay? So an individual individual protein can actually oftentimes be dissolved into water just like salt can. Now, let's go on to take a look at this in regards to the idea of things being hydrophobic and hydrophilic. So again, a refresher, hydrophilic is a substance that has an affinity for water. Hydrophobic is a substance that does not have an affinity for water. An example of this would be oil molecules. So you can think of vegetable oil or other various oils. These oils have all nonpolar bonds. So consequently, they cannot form hydrogen bonds directly with the water. What happens here is this is going to cause those hydrophobic molecules to be clumped together. Okay, and an example of this would be what happens in cell membranes. And we'll go deeper into that in another chapter. So, how this works is in the universe, things that are highly ordered tend to become more disordered. So think about a bucket of water, you pour it on the ground, it spreads out. As it spreads out, it'll start to evaporate and gets even more dispersed and more disordered. This is a property that we call entropy, and this is just a fundamental truth about the universe. Everything moves towards an increase in entropy or more disordered. So now we're going to take a look at a couple of nonpolar molecules. So here's the little fat molecule, and here's another fat molecule. And here is water around it. Just like at an air-water interface, the water molecules that are in contact cannot form hydrogen bonds with the nonpolar surface, so it has to form this cage around that molecule. And you can see over here, we have another cage around another molecule. Well, this is a lot of order. And remember that we are moving towards more disorder or an increase in entropy. So here is a low entropy. One way of achieving higher entropy is if we squeeze these two nonpolar molecules together and form a single cage around both, it actually takes less water molecules. So now this water molecule, this one, this one, this one, this one, this one over here, they're all free to be disordered. And that is what the universe wants. So consequently, when you take oil and you shake it up in a mixture with water, it starts off as a bunch of separate things, but it'll always clump back together. Now, don't confuse water cage with hydration shell. Okay? There's a similar thing happening in that it's being surrounded by water, but in this case here, while these water molecules do want to leave the sodium, it would prefer to be more disordered. The ion itself, the attraction towards that ion is so strong that it overwhelms this entropy urge. Okay, so the energy is implicit with the ion to hold those water molecules to it. Okay, so here we have water cages, here we have hydration shells. All right, next thing we need to talk about is this idea of solute concentration in aqueous solutions. So again, aqueous solutions, meaning that water is the liquid that we are going to dissolve something into. The solute is the thing that is being dissolved. When we are doing chemical experiments, we need to have a way of understanding how many molecules of the solute are in the solution. Because remember that a lot of reactions require specific ratios of one thing to another. And if we want to add the proper amount, we need to add it in the right ratio. So we need to know how many molecules are in the solution. To do this, we first have to know the molar mass. And this is simply the sum of all of the masses of all the atoms in that molecule. So you take, in the case of a salt crystal, you would take the mass of sodium and the mass of chloride, and you would add that together. That gives you a molecular mass. But salt is probably not the best way of talking about it, but you could think of it in terms of water too. We have one oxygen and two hydrogens. We just have to add the mass of each atom together to get the mass of the molecule. All right, now, the number of molecules is usually measured in this unit called a mole, okay? And a mole is equal to 6.02 times 10 to the 23rd power molecules, okay? So this is billions and billions and billions of molecules per 1 mole. You might ask yourself, well, why 6.02 times 10 to the 23rd? Well, it just so happens that 1 gram of hydrogen has that many molecules. So this becomes kind of the standard at which we measure everything against. So here, this is 1 mole of hydrogen. All right, so this number here, this 6 times 10 to the 23rd, is called Avogadro's number, and it also is the foundation of this unit called a Dalton that we can relate to grams. Okay, so here we have a Dalton is equivalent, so there are 6 times 10 to the 23rd Daltons per 1 gram. Okay, it gives us a way of converting between grams and Daltons. Now, we also have this concept called molarity, and this is the number of moles of a solute per liter of solution. Okay? So if we have a 1 molar solution, we have 1 mole of whatever solute is present in 1 liter. Utilizing molar concentration allows us to do some complex math. So making sure we have the right ratios of things. So when we have things that are the same molarity, if you have 1 milliliter of a 1 molar solution of X, it has the same number of molecules as 1 milliliter of a 1 molar solution of Y. Now, I don't want you to be overly concerned with this whole process and how you would actually do this. That is something you will learn all about in chemistry. What I want you to understand is kind of the concept of a mole and that 1 mole is 6 times 10 to the 23rd molecules. And the idea of molarity, in that if you have 1 mil of a 1 molar solution of X that has the same number of molecules as 1 mil of 1 molar solution of Y. So if you were to add this mil and this mil together, you would have equal parts of X and Y. All right, so for concept 3.2, the 4 emergent properties of water that contribute to Earth's suitability for life. Those 4 properties are cohesive behavior, ability to moderate temperature, expansion upon freezing, and versatility as a solvent. So first, remember, this is all based on the idea that water is polar and that it can hydrogen bond to itself. Because it can do that and also hydrogen bond to other things, it has a cohesive nature and also has adhesion. So these water molecules can adhere to the side of these water channels and also to each other and draw the water up a tree. Or in the case of this insect on water, the fact that the water at the surface can only form hydrogen bonds with the water below it, so the water on the surface is a little bit more structured than the water underneath it, and when something presses into it, it takes a little bit more energy in order to break that. So we have insects, or arachnids in this case, or other insects walking on water. We also talked about how when water freezes and becomes ice, it actually expands. That is because it now has, every molecule has 4 hydrogen bonds, and it has these empty gaps present. To where if you only have 3 hydrogen bonds, or at least partially 3 hydrogen bonds, you can pack the liquid water a little bit closer together. We talked about how it can be a solvent. Water can be a solvent. So if we have something like salt, an ionic compound, these polar water molecules can form a hydration shell around those ions and pull them off of the crystal. We also had the idea that when we have nonpolar substances, it acts a lot like the surface of the water here, in that the water has to form a very ordered cage around each of these molecules. But we also know that that takes a lot of order. The world likes disorder, so if we squeeze those 2 molecules together and build one slightly bigger cage around both of them, we can free up some water, letting it go crazy. We also went into the concepts of molar mass, which is simply the sum of all the masses of the atoms in a molecule. That 1 mole is equal to 6 times 10 to the 23rd molecules, and that the concept of molarity, which is a 1 molar solution, has 1 mole of that solute in 1 liter of solution. And we can utilize that to combine reagents to get fixed ratios.